This is the third part of chapter 27, circuits. We have learned capacitors and resistors and how they combine. So we're going to have a review. And then we're going to introduce RC circuit charging of the capacitor, RC circuit discharging of capacitor. The really important thing in this part is what we call the RC time constant. This is a Greek letter, tau, that equals to the resistance R multiplied by the capacitance C in the unit of seconds. RC time constant is important because it represents the transition from a steady state circuit where the current is a constant to a oscillating circuit. So that represents the transition to modern communication technology. So modern circuits are the ones that oscillates, and what matters is the frequency, which is a lot more important than the intensity of the currents. We will look at the RC circuit application by looking at the experiments later. So here we look at this. We used to have resistors combine to make a circuit. And we also look at how different capacitors combine to make circuits. Only resistors, only capacitors. RC circuit is we have both resistor and capacitor combined in the circuit. There's a switch, there's a power supply. The simplest RC circuit is one with one resistor and one capacitor. This is a circuit that causes the current to change with time instead of, for example, like a resistors circuit, as soon as you close, like the light bulbs, it's on, and when you open the circuit, it's off instantly. But with a capacitor added, now we'll see it'll change with time. Let's look at the charge. When we close the circuit to point A, the potential difference on the EMF will cause the current, which represent the positive charge, to flow. And therefore, the upper side of the capacitor will start to have positive charge. And the lower side, for the same reason, will have negative charge. The total charge on the capacitor equals to the capacitance multiplied by the EMF, which is the voltage of the battery, multiplied by 1 minus an exponential number, here e to the negative time over R times C. So that's for charging. We'll come back to talk about discharging. Let's take a look at this in a graph. So this curve in red color here represents the charge on the capacitor. This charge starts to be 0 as the circuit is being closed. When the circuit is being closed, there's no charge yet on the capacitor, and there's no voltage yet on the capacitor. And the current flowing out of the power supply is the battery's voltage divided by the resistance in that circuit. As current flows, more and more charge accumulates on the capacitor. So you see the total charge here in the red color keeps increasing. As time increases, the charge increases, and finally the plateau becomes capacitance times the battery's voltage. At that point, the capacitor has the same voltage as the battery. That's what stops the current. And charge no longer moves and the current becomes 0. So here represent how the charge of the capacitance increases. So if we go back, what about discharge? And now the capacitor has a steady state amount of charge. Then we say this capacitor is charged. If you disconnect the circuit, the charge will remain on the capacitor. So that's what we say capacitor is a device that can store charge. So the charge will stay on the capacitor. Now, what if we remove the battery? Instead, put the switch on point B. In that case, this capacitor is now being charged, positive on top, negative at the bottom. There's a voltage, or in other words, there's a potential difference. And that potential difference will drive this current to flow in this circuit, going out from the higher potential back to the lower potential. The current will keep moving until the charge on the capacitor is reduced to 0. At that point, we say this capacitor is discharged. Basically, if we touch these two wires, the charge on the capacitor will be eliminated. So this is the discharge function. This is the Q represent the electric charge on the capacitor. That equals to Q0. That's what it starts with at time equals to T equals to 0. And the exponential time over RC constant. Let's take a look at this in a graph. So as time goes on, the voltage on the capacitor will keeps decreasing when it's being discharged. Because the charge is removed, so is the capacitance. Remember, the capacitance is a device constant. Okay, so here's the discharge. In this curve, because it's an exponential curve, when T equals to R times C, the charge becomes 37% of the initial value. So this is a DC RC circuit discharge. And what's called the RC constant is the value of resistance multiplied by the capacitance. It's in the unit of seconds. So this value is very important because that's a circuit property or circuit constant. For a circuit with a capacitance and the resistance, RC is a constant. That means if you build a circuit, then this circuit has an intrinsic characteristic property that is time. So that has to do with the circuit oscillation, and that's the basis for modern communication technology, which means when there's a circuit is built, there's a time property that's important to it. So we talked about RC circuit part 3. So what we did is that we reviewed how resistors combine, how capacitors combine. And here we combine mixing resistor and capacitor. That's what we call RC circuit. We talk about charging, that's to add charge to capacitor. Discharging, that's to remove charge on the capacitor. And RC time constant, which is a device constant for the RC circuit. This value of time that equals to resistance multiplied by capacitance is a really important property. And this is the turning point from steady state current to oscillating current, which represent the basis for modern communication technology.